Hello and welcome back, student. We'll start with the third part of gas chromatography. In first part, we have studied the basic principle of gas chromatography. Then we have studied in the second part, we have started with the instrumentation. In instrumentation, we have studied the various gases, carrier gases we use in the chromatography, gas chromatography. Then we have studied the gas control panels. Then the various methods by which the sample injection is done. Then the columns, various types of column, plot column, packed column, and tubular columns, open tubular columns like capillary columns. Then we have studied the detectors which are used in the gas chromatography, and lastly, the evaluation process of your gas chromatography. So we'll continue with the evaluation and some theoretical aspects of evaluation. So in evaluation, we have studied that either we are studying this retention time as a qualitative parameters and retention volume or area covered under the peak and peak height. We are using it for the quantitative estimations when we are getting the chromatogram. Chromatogram is a retention, it is a time versus response graph, and that is used for the further processing on the gas chromatography. So we are either studying here retention time, retention volume, separation factor, resolution. So this parameter used in gas chromatography, first we will see the definitions of retention time. The difference in the time between the point of injection and the appearance of peak maxima, it is called as the time required for 50% of component to be eluted from the column. It is measured in minutes or seconds. So if you see, this is TR. TR is a retention time. So it is a peak of elution of the substance from point of injection. Initially, we'll get the TM. TM is a time of for the solute or the solvents to elute out from the column. Then we are taking the adjusted retention time, that is TR minus TM, which will be equals to the retention time of your solute. So this is your retention time. Then we'll see the second parameter which is used in gas chromatography is the retention volume. The volume of carrier gas required to elute 50% of component from the column. So the retention volume is the retention time multiplied by flow rate. So what is the flow rate that is adjusted, that will decide how much retention volume will be there. So we are taking retention volume for many quantitative estimation process. Then retention factor, the ratio of partition coefficient of the two components to be separated. How much substance is there into your solute and how much substances is there in your stationary phase, that is to be taken as a separation factor that will decide the efficiency of your column. So retention time of non-retained component can be taken as TR2 minus T0. T0 is a first the volume or the time required to solvent to come out is a T0 you consider. TR1 is the retention time for first solute and TR2 is the retention time for the second material. So TR2 minus T0 divided by TR1 minus T0. So retention time of non-retained component can be determined by using this technique. Then parameter used in gas chromatography include resolution. It is the measure of extent of separation of two components and baseline separation achieved. It is determined by the formula. So various theories are there: rate theory, plate theory. We will see this rate theory and plate theory in the subsequent slides. But now you see this resolution. The resolution that is denoted as RS. Okay, so how much these two peaks are separated from each other, that is called as a resolution. So TR2, 2 into TR2 minus TR1 divided by WB, that is width of the peak. Okay, so width of peak for the first component and second component. So it should be minimum so that the more resolved peaks can be obtained, which are having delta TR values, that is difference between this TR1 and TR2, they should be separated more. So TR2 is taken as a 4 sigma, WB2 is also taken as a 4 sigma, and RS is to be considered as a 1. Tm is a retention time for a solvent molecule. So generally, this resolution is measured in form of the height equivalent to the theoretical plate. So what is HETP? It is the distance on the column in which the equilibrium is attained between the solid in gas phase and solid in the liquid phase. So this height equivalent should be minimum to get the maximum efficiency of separation, and for that purpose, if it is minimum, maximum number of the theoretical plates can be kept into the column. So larger the number of theoretical plate and smaller will be the HETP, more efficient will be the column for separation. So HETP can be given as a length of column divided by n, where n is the number of theoretical plate. So we'll consider the equation of HETP equals to 16 into x2 divided by y2. So average volumetric flow rate, that is ml per minute, F, can be estimated by measuring the flow rate extending the column using the soap bubble meter. Some gases dissolved in soap, so you have to take care that what soap solutions you are using. Generally, we are measuring the retention volume of your first component and the second component. So VR equals to TR into the F. F is a flow rate, okay, of the retain divided by F. Vm equals to Tm into F. F is a flow rate for the non-retain. But measured VR and Vm depends upon pressure inside the column also. So these are certain factors to be considered. So in more detail, we see these factors. So now first is your plate theory, or it is a hypothetical theory. So in which the column is divided into the number of plate adjacent imaginary segments called as the theoretical plate, where the equilibrium has been reached. Within each theoretical plate, analyte completely equilibrate between the stationary phase and the mobile phase. So theoretical plate, the number of theoretical plate can be determined by the following equation. N equals to 16 RT upon W2. So where N is the number of theoretical plate, RT is a retention time, and W is a peak width. So generally, the peak width, half peak width is taken for further calculations. So plate theory did not suggest the way of improving performance of the column. Hence, rate theory came and is widely used now. So what is the rate theory? Efficiency of column is expressed by number of theoretical plate in the column, or it is called as HETP. All of you know. If HETP is less, the column efficiency increases. If HETP is more, the column efficiency decreases. So we can write HETP equals to L by N. L is the length of column and N is a theoretical plate. So it is inversely proportional to the height of the HETP is inversely proportional to the number of theoretical plates. HETP is given by Van Demeter equation in the rate theory as HETP equals to A plus B upon mu plus C into mu. So this is called as a Van Demeter equation, where individual terms are included. The A is known as the Uday diffusion term or multiple path diffusion term, which arises due to the packing of the column. So this is related to the packing. What is the size of packing and what is the shape of packing? That parameter is included in the A term. B term is called as a molecular diffusion term, which depends upon the flow rate, and C term is effect of mass transfer. It is dependent upon how much mass transfer is occurring. So that is called as a longitude. B term is called as a longitudinal diffusion term, and C term is called as a mass transfer term, which depends upon flow rate. So as the flow rate increases, the mass transfer increases, but as the flow rate increases, the molecular diffusion decreases. So efficiency of your column depends upon the flow rate and the total contact time between the mobile phase and the stationary phase. A symmetry factor means the shape of the peak. Chromatographic peak should be symmetrical about its center. If peak is not symmetrical, it shows fronting or tailing. So what is fronting? Fronting is due to the saturation of stationary phase and can be avoided by using dilute samples, less quantity of the samples, and tailing. So you see this is the fronting and tailing diagrams. So what is tailing? It is extending the latter part of your peak, and it is due to the more active absorption sites and can be eliminated by support parameters. Support pretreatments. Factor influencing the separations. What are the various factors? Like your first is vapor pressure. The lower the boiling point is, the higher the vapor pressure of the component and shorter retention time. Usually is because the compound will spend more time in the gas phase. Second component which is affecting the separation is the polarity. If polarity of the stationary phase and compounds are similar, the retention time increases because the compound interacts strongly with the stationary phase. As a result, polar compound has long retention time on polar stationary phase and shorter retention time on non-polar columns using the same temperature. What is the effect of column temperature? So column temperature, as the temperature increases, retention time decreases. But the separation will be very poor because most of the compound stays in gaseous phase itself. The best separations are usually observed for temperature gradient because the difference in polarity and boiling points are used here to get the gradient illusions. The next factor is carrier gas flow rate. A high flow rate reduces retention time, but a poor separations would be observed as well. The column length. A longer column generally improves the separation. The trade-off is the retention time increase proportionality to the column length, and a significant peak broadening will be observed. The next factor is the amount of material injected. As we have seen, the fronting occurs due to the higher concentration of material which is injected. If too much of the sample is injected, the peak shows significant tailing, which causes poor separation. Now we'll see the application of gas chromatography. In qualitative analysis, gas chromatography is used by comparing the retention time or volume of sample to the standard, and by collecting the individual component as they emerges from the chromatogram and subsequently identifying this component by other method, qualitative analysis can be done. In quantitative analysis, the area under a signal or area under the peak component illusion peak is proportional to the quantity of the detected component, which is called as a response factor of the detector. So volatile oil in official monograph gives chromatographic properties for some drug. Example, mm, distinction between anise oil from star anise and that from pimpernel anisum. So that can be done by using the gas chromatography. Gas chromatography is also used for separation of fatty acids derived from the fixed oil. The other miscellaneous applications include analysis of food like carbohydrates, proteins, lipids, vitamins, steroid, drugs, and pesticide. Reduces pesticides residues and trace elements. It is also used in the environmental science for detection of the pollutant like formaldehyde, carbon monoxide, benzene, and DDT, etc. In dairy industry, it is used for analysis of dairy product and finding the rancidity. Separation and identification of volatile matters, plastics, neutral and synthetic polymers, paints, and microbiological samples can be done by using this gas chromatography. In inorganic, it is also used for analysis of certain compounds. So here we have completed all gas chromatographic chapter. Thank you and see you in the next video. Happy learning, friends.